So hello, everybody. We're welcoming Dr. Megan Williams from Chile today, who is going to talk about, that's too long for me to read that whole title.
Estuaries.
Yeah. So Megan is an assistant professor at the Catholic University of Chile in Santiago, but they also have a marine lab down on the coast at Las Cruces, ICIM, and I'm not going to say it all in Spanish, but it's very similar to BML. And so we have quite a lot of connection with Catholic University and with ICIM. And so it's really nice, in addition to what Megan brings, is she brings these developing connections with that university and marine lab. Megan got a PhD from Berkeley. I forget in a year, it doesn't matter too much. Working in civil and environmental engineering. Actually worked in Pescadero Lagoon in San Mateo County, and then did a postdoc plus, I guess, at the National Ocean Center in Southampton in the United Kingdom. We did a bit more physical oceanography, but still really stressing estuaries, and has been in Chile now for what, like 4 years, probably 2019 or so. Recently joined the Catholic University, which is great because it's nice having a person interested in estuaries there, and multiple cool projects. I'm going to pass it on to Megan. You can mention, I guess you'll mention some of them in your talk, but feel free to expand on this introduction if you'd like to tell people anything more about you. I think I covered the key things. I mean, your field would be physical processes, I guess, of estuaries and coasts.
My field would be physical processes of estuaries and coasts, with some dabbling in resilience and coastal change, and some dabbling in biology and wetland ecology.
Cool. Oh, that's a cool thing. So Megan has a joint appointment in biological sciences and in engineering. So that must be an interesting game to play. But it does point to an interesting cross-disciplinary perspective. So without further ado, it's you.
Thanks, John. And thanks so much for having me. This beautiful coastal laboratory at UC Davis. So what I want to talk about today is watershed coastal connections through Mediterranean semi-arid estuaries. And what that really means is I'm going to talk about estuarine dynamics. We're going to talk about physics. We're going to talk about some anthropogenic influences. And I put the words potential ecological consequences up there. And that's really a talking point. Because I'm coming from a physical background with physics and engineering, but starting to work more in spaces that are ecologically very important, and we're seeing some drastic changes. And I'm hoping to have some conversations with you about some of the things that you see in the work that I'm going to present. Like John said, I'm a joint appointment in hydraulic and environmental engineering and biological sciences at the Pontificia Universidad Católica de Chile, where I've been since just March of this year, and visiting Stanford for the semester. So thank you to Stanford as well. And obviously this is work of myself, but also colleagues, including several who are probably not on there, and work with Americans, Chileans, and I think that's it. So here is a picture of the Maipo estuary. This is in central Chile. And what you'll notice is that Chile and California, we have the same coast. We have a long coastline, we have an upwelling system, we have Mediterranean climate. And so really a lot of the things we're talking about are mutually applicable to California and Chile. And in some cases, management is better here, there, or there, and so there's also some nuances. So I'm going to start with my conclusions so we can see where we're going, and for those of you who have to duck out to lunch, you can go ahead. So what I want you to get is that flow through Mediterranean and semi-arid estuaries is episodic. There's a range of temporal scales that we need to be considering. For example, sediment flux between estuaries and wetlands has a strong infragravity signal. And that these systems are highly vulnerable to anthropogenic impacts, including drought, climate change, and these effects that are exacerbated by human impacts. I'm going to start with an introduction to barbelled estuarine dynamics. What is a Mediterranean and semi-arid climate? What are the forcings that are important? Tides, waves, how do these contribute to inlet closure, and tidal dynamics? Here is a picture. This is another small estuary in Pichicuy in north central Chile. This is ranging on the more semi-arid or arid part of the coast, and you can see there's a small wetland, and there's not a connection to, there's not a surface connection to the ocean. So here, I promised lots and lots of pictures. On the top, we've got the Maipo estuary. Down here on the bottom left is the Pesquería estuary, like John mentioned, it's in San Mateo County. The Pichicui, and then a picture from a couple of weeks ago, Sentinel-2, image of two river plumes in central Chile. And so what you can see is that we've got a lot of different scales. We've got inlet closures happening. We've got no connection to the ocean. We've also got these massive river plumes that are stretching. I'm going to say hundreds, but probably tens of kilometers off the coast. There's an intertidal system. So here's a smattering of pictures of Mediterranean estuaries. Here is a quick geography of what is the Mediterranean, where are Mediterranean climates. So central Chile on the left, these are the kind of Köppen climate classifications. California, the Mediterranean, South Africa, and there's also Mediterranean climates in Australia. And what's important from an estuarine and from a watershed ocean connection is the climactic forcing that we see. So if we remember back to our climate geography classes, what is a Mediterranean climate has to do with seasonal precipitation, and that has to do with the oceanic highs. And so in the austral summer or boreal winter, so winter here or summer in Chile, we see that the high pressure system right off the coast of California sort of moves onshore, it strengthens, and obviously it doesn't rain here in the summertime. Flip that over in Chilean summertime and Californian winter, the high pressure system either moves or weakens in the northern hemisphere, and in the southern hemisphere it moves, strengthens or moves onshore, and so same thing, we're blocking the precipitation. So what does that mean that we only have seasonal rainfall in Mediterranean climates? It means that that all of our rain comes part of the year. Maybe in snow, maybe in precipitation, and we have a long, dry summer. So there's a vast difference in the forcing that we see at the coast. This climate forcing is also exacerbating what we're seeing in terms of drought in California, drought in Chile. Here's a picture of the Mediterranean, and you can see the high pressure. I think it's a high pressure mean in the figure on the right, in the contours, and the coloring is an anomaly, and it relates to a precipitation anomaly that is showing up on the picture on the right. And so what we're seeing is that some of these climate dynamics are making big changes in terms of what sort of precipitation we're seeing in Mediterranean sun. So that was Mediterranean. Same thing in Chile. We're in the middle of we're undergoing a drought that started in the year 2010, which has to do with PDO and anthropogenic impacts, but really is what you can see a strong correlation between the atmospheric effects that cause the drought. So there's some nice work on why is it so dry in central Chile and what's our future going to look like, and the predictions are we will remain dry, although we've had some big storms this past month or so. So we have a seasonal precipitation in these climates, and how does that translate to something that we feel at the coast? We can first think about the stream flow that's coming to the rivers. So here is a picture of the Aconcagua watershed. I'm going to show you data from two stream gauges, Chacabuquito, which is in the Andes, and Romeral, which is a lot farther downstream. And what you can actually see in this image is the area, the sort of green area in the middle is all agricultural land. So there's very high agricultural pressures in Chile, much like there are in California. And so our seasonal precipitation might look like this. Here's daily stream flow at Chacabuquito. Remember, this is the high elevation stream gauge. You can see that all of the stream flow is happening in the summer, in this case, where we've got snowmelts. And if we go farther down the hill in Romeral, where it's we have a more mixed pluvial climate, we can see that the winter rain shows up as some stream flow, and then also the summer snows. And so we can clearly see that there's a strong seasonality to the stream flow that we're seeing in the watershed and thus at the coast. That's obviously going to impact the estuarine dynamics and the coastal dynamics. So we've got Mediterranean climates, seasonal precipitation, and episodic stream flow. Also important on our coast are tidal ranges. In general, the Mediterranean climates see micro tides. So we've got 1 to 2 meters in general in all of these coasts. And we've also got a big but not huge wave climate that is able to transport and cause effects from the ocean. So how does this translate into what we see on Mediterranean coasts? Here's the Pescadero estuary. This is before drones. This is Rusty Holloman's kite camera. And so here's a picture from where the Pescadero estuary is open to the ocean, and another one where the Pescadero is closed. And so what we see here is we've got a seasonal precipitation, we've got tidal influences, and then we've also got this wave climate. And it's actually the waves that push sand on shore and close the inlets of many of these small estuaries. Many of you are familiar with the work that Dane Behrens did as a PhD student at this institution, where he studied the Russian River and came up with a really nice classification of what is causing closure of the Russian River inlet. And so what Dane showed is basically we've got a balance of things that are scouring, which is quite quantified as inlet flow, and the wave climate, which is pushing waves, pushing sediment on shore. And I think that he was able to do some predictive work to show when the inlet will actually close, and it happens when we've got these big waves that are pushing sediment on shore and small flows of the inlet, so small tidal flow and small river flow. I'm going to get back to this sort of concept in a little bit. But so we've got this dynamic system, which might be totally closed, it might be totally open, but really most often we have kind of a constricted system. This is the Aconcagua estuary in Chile again, and what you'll see is clearly there's some tidal flow coming through here, but I'm not going to guess that there's 1.5 meters of tidal range within this estuary. So that ends up being dynamically important when we're considering the physics of these systems. So here's work from my PhD in the Pescadero estuary, and what we saw, if we just look at the tidal amplitude in the estuary compared to the tidal amplitude in the ocean. So in gray here we have the San Francisco tide, and in black and red I've got the tidal measurement within the estuary. Instead of having that full 1.5 to 2 meter tidal range, it was maybe something like 90 centimeters some days. And it's a dynamic system where actually we have part of the tide, the ocean and the estuary level are about the same, and part of the tide, because that sandbar is at the mouth, because there's so much sediment transport on shore, part of the tide, the ocean is actually dropping below the inlet. And so we, instead of having kind of a normal tidal estuary, like you think of San Francisco Bay, or we think of the Columbia River, we actually have kind of an estuary that becomes an estuary, and then it becomes kind of a draining reservoir, depending on these conditions at the inlet. The other thing that you'll see here, if you look at those pictures or any of these pictures of the coast, is on the ocean side, we've got waves breaking. And you can see that in the estuary, there's not quite as obvious a signal of these swell or wind waves, but you do see some sort of surface expression. And so what we see in these estuaries is what are called infragravity waves. So quick reminder of what those are. If you put your blanket out on the beach and get comfortable right next to the water line, and then 2 minutes later, everything gets soaked, you're experiencing an infragravity wave. This is a low frequency, between 30 seconds and 5 minute oscillation of the water line that is present on sandy beaches. And what we actually see in these small estuaries is the high frequency, the 5 second waves get filtered out, but this low frequency is able to propagate in. This is a really lovely set of data from Madeline Harvey's work in the Los Penasquitos estuary, which is near San Diego. And she's actually got here pressure sensors from the coast all the way upstream. And what I want you to see, the 4 spectra here have spectral energy, and she's looked at the high frequency kind of swell waves and the mean for gravity. And what you can see is that as we move onshore, the high frequency stuff is all filtered out, and we have this lower frequency for gravity that is making it in. So this is one of the features of these estuaries that we see in the velocity. We see in the pressure records. Here's another one from the Maipo estuary in central Chile. Just the pressure measurement, and we're seeing again at high tide, we've got this low frequency infragravity energy, and as the tide goes down, that energy is cut off because we've kind of got this draining system. Okay, so that's the background. Everybody is now an expert in barbell estuaries in Mediterranean climates. So what I want to ask is, okay, great, we've got this understanding, but what do we need to know? What are we missing? And what is the future of these systems? And so one of the questions that I'm looking at in Chile is this question of suspended sediment dynamics. And largely because nobody's done it, or there's very little work in small systems, and also because of the changing sediment loads that we're having to the coast. So there's a lot of work looking at what is the sediment loading and how is it changing to the coast, and basically everywhere it's changing, and maybe it's being reduced because we have stream flow diversions, we have dam construction. Maybe it's increasing because we're cutting down trees, we're increasing deforestation, or for agriculture. And so there's a lot of anthropogenic processes that are changing sediment loads at the coast. And when we actually are thinking about what's happening at the coast, we need that sediment load from the watershed to help basically maintain our coastal wetlands to sea level rise. And so there's a lot of work out of the Western Ecological Research Center here in Sacramento, looking at the prediction, looking at the future of California and Mediterranean wetlands, depending on sediment and sea level rise. And so we want to look at that question in the Maipo estuary. So one of the important things in wetlands in Mediterranean climates in comparison to wetlands in tropical environments is that our wetlands have very low organic content in their soils. And so what that means is if you're in Brazil or Panama, maybe most of your sediment is plant matter growing and decaying, whereas most of our sediments in this kind of estuary are actually coming from the watershed. And so if we don't have those watershed sediments, then we are sort of predicting that we're going to be losing our coastal wetlands. And so one of the questions we have is how are sediment delivered from the estuary, i.e. from the watershed, to the wetlands? And so in this, we're focusing on one estuary. This is the Maipo estuary in central Chile. And this is arguably one of the most important watersheds in the country. You'll see here the watershed. The city of Santiago, which is in gray in the middle, is home to like probably 40% of the country. It's a city of 7 million. The two main tributaries of the Maipo, the Mapocho and the Maipo, are shown in blue, including the Mapocho, which passes directly through Santiago. And all of the green area is agricultural cropland. Some of the best wines in Chile, you go to Trader Joe's and grab a bottle of Chilean red wine, it may say Maipo Valley on it. And so thank you very much. You're taking my water from my estuary and bringing it to California. So this is it's a dynamic and politically tricky little estuary. And so why pick an easy one to study? But it's also we've got a lot of loading. We've got sediment that comes down from the Andes Mountains, and we've got fishermen and a port to fight with too. But let's focus on the physics. So here is the estuary. There's the city of San Antonio to the north, and there's a large intertidal flat, and large by Mediterranean climate. This is not large if you were to compare to the UK. But we've got these intertidal flat system, which is shown here in red and there as well. And there's the inlet of the Maipo Estuary, which you can see has this wave climate on the outside. You can see a flow here. And you can also see that there's, hopefully you can see that the river flow is a little bit turbid. So we've made measurements at this location. And everything I'm going to be showing you is going to have positive X towards the wetland and positive Y towards upstream, downstream. Yeah, if somebody can give me the secret to how to show brown on slides, they always look great on my computer and not so much on the presentation. Right, so here's our estuary. Here's our arguably small but possibly important wetland that you can see here in the background. And here is a tripod that we put out. It had an ADV, a turbidity sensor, and a small CCD. And there's me. It's a muddy flat. And when we first did this work, we realized that the only people who could actually get out in the flat were myself and all of the female students, because all of the guys were just had enough weight that they made it to. I don't know if you can see, there's like a kind of scar in the middle of that mud flat, which is where all of the male students made it there and then fell over. And we said, okay, we'll take it from here. So challenging and lovely work that we do in Chile. So here's this intertidal flat, and on the top here, there's a plot of in blue is the estuarine water level, and in black is the tide gauge at the San Antonio port. And so what we can see here is clearly there's about 80, 90 centimeter tide within the estuary, and there's a larger tide outside. And on the right, there's 3 tides of measurements from September of 2021. If we zoom in on these 3 high tides, we can see that there's a strong infragravity signal in the pressure level. And so this on the figure on the right has a 30 minutes between each time tick, and you can see that there's 5 or 6 or 7 little oscillations. And those are maybe 10 centimeters, 15 centimeters. And so as the tide's coming up, it's coming up in one spot like this. And I'll also show you that as the tide is coming up, we see a very strong difference between the ocean water and the river water in terms of turbidity. So if I were being in the world of real science, we present this as clearly our hypothesis, and this is clearly why we need to study this. But in the world of honest science, we were out there making some measurements, and we saw something cool, and so that's where this came from. So I will let you guys start from the let's see something cool instead of this is definitely a hypothesis we had. So this is a drone image. You can see on the bottom right is the place where we had the intertidal frame. You can see footprints and some points where we're doing ground control points to rectify this image. And this is the rising tide. This is early first drone video on the 10th of September, 2021. And what we have here is 4.5 minutes compressed into, I think, 12 seconds or so. It should be fun, right? So what we're seeing is as the tide is coming up over this flat, we've got a progression of maybe a moving tidal bore or a moving infragravity bore that's coming up and over that flat. And this movement like this is happening on about 2 minutes or so. So if we go, I think this is yeah, so this is maybe a few minutes later or maybe 1 minute later. And the same thing. Do you see movement? Okay, well, that one, I was going through. Right, so a few minutes later, we see the tide is coming up a little bit. And what we can start to see is there's kind of a dark patch that we see on the edge of that water plume, and you can see kind of something kind of advecting around. Knowing that this is not the easiest color to look at, I've given it a really good Instagram filter via MATLAB, and so hopefully we can see here a little bit better that there's actually kind of a mass of darker water that's being advected or moved around with these infragravity motions that are coming on shore. And this one just a little bit later in a few minutes later, the tide is coming up higher. And what we can actually see here is that there's this kind of turbid area. And back here, we're actually able to see, it's so clear that we can see the tidal flag. So what we see is that clearly there's a lot of spatial dynamics here. We've got flow kind of going through the channels. But what I want to focus on is this big transport of this mass of turbidity or mass of sediment that we're seeing in these videos. So here's, if the video doesn't work, here's the water line. Here's a region of very high turbidity. And there's our measurements of the ADV, the OBS, and the CTD on the mudflat. So we've got video evidence. We know that this is real. Let's look at the data now in the appropriate science way and ask what's happening. So what we see here, I've got plotted turbidity, I've got velocity, and I've got a depth measurement. The turbidity measurement the peaks are about 0.8 grams per liter, which is very high. The calibration is a mess, so it's the turbidity flux at this point in time. We see these big turbidity peaks. We see the velocity peaks, which correspond to what we're seeing with our eyes, and we also see this movement of depth. We have here 15 minutes plotted. So what we're seeing in these measurements at the intertidal frame, if we look at this red line, we've got the onshore towards the marsh velocities, moving slow towards the marsh. But you can see at that point in time, the turbidity at that station is very low. And then we've got flow reversal, and then there's we're seeing that plume of turbidity ejected back past our system. And so what we're seeing is this movement. It's not local resuspension. It's some sort of further up the marsh resuspension and movement of this sediment plume on this spot. So cool from it looks great from the drones, and there's these really sharp signals. So interesting from a sediment perspective, but what we're really trying to get at is this important? Do we need to consider this if we want to consider, we're thinking about the future of barbless estuaries and the wetlands that rely on sediments from the watershed? And so to do that, we're going to do we're going to try to look at the turbidity flux. But first, just to verify that these measurements are seemingly in agreement, here's a still from the rectified image. And if we take a slice through that dotted line and look at it in time, so on X we've got the meters on that line, and Y the time in seconds, and so we can see I guess orange X's are tracing the front of that high turbidity zone, and the triangles have got the back of that turbidity zone. And so if we look at this in time, we can see ejection of this plume or this high sediment, high turbidity area onshore and offshore. And we can calculate, we can track those and get a velocity similarly about 0.5 meter a second of movement of those edges. We're seeing the infragravity velocity moving sediment up and down the intertidal flat. But is there net transport? Is this important? So here we're going to do a cumulative turbidity flux. Call it a sediment flux, but it would have to be better calibrated. So we've got velocity in blue towards the wetland, in red upstream. We've got turbidity. We can look at basically multiply them together and take an integral. And so what we see is that in the upstream downstream, towards the river, towards the ocean, we're about neutral, about net zero. in this measurement location, but there is a very substantial flux towards the wetland, especially at the very beginning of that flood tide. And so we want to explore this in further details. And so what I've done is a sort of Reynolds decomposition to separate the mean, which is basically tide, and the infragravity terms, which are these oscillations that we see. And so we can separate mu into a mu mean and an infragravity component. We can see that the mean flow in this location is very, very, very small, and the infragravity component is humongous. Same thing, the turbidity, it's not a average, it's a running minimum. So I wanted to separate off the background and these infragravity peaks. And so if we look at these separate components of these turbidity flux terms, we can separate out each individual bit of is it mean flow, is it infragravity, and how they multiply together. And what we see is there's two dominant terms. One is the background tidal riverine transport of the infragravity sediment flux, and the other one is the transport of the infragravity sediment by the infragravity velocities. So what we see here in these terms, we've got a background. So we've got this at the start of this tide, we've got these big pulses of flow along with these pulses of turbidity that, as we average through, we see them being dynamically relevant, and also the background flow multiplied by these big peaks of turbidity also become important. But however, the infragravity, these like strong movement of this turbidity field is very quick, very episodic. Start of the flood, and then it almost becomes constant. And so we need to look into a little bit more details there. And so what we see, why is that? It's because the turbidity signal starts out very, very high, and then starts to drop off. And so you look at this orange figure, you see high turbidity, and then still an elevated turbidity with those infragravity movements, but not nearly as high. So the obvious thing to think about is a bed stress reduction. And what we see is if we do a proxy, there's a little bit of a reduction in bed stress. But the thing that I have not mentioned at any point in time is salt. I suppose we saw tidal intrusion something at the very beginning. So I've got two moments in time where I was out in a wetsuit in 80 centimeters of water with my CCD making profiles. And so both these images on the right are profiles of salinity in 50 centimeters of water. The first one on the top, you see these big turbidity peaks and pretty low salinity, and also the water column is almost completely unstratified because still river water that's coming out. And so we see like the very first little, in that little arrow, we see the very first bit of salt moving up and over the salt flat, but generally very high turbidity. And then if we look 15 minutes later, all of a sudden we have between salinity of 5 and 35 in 50 centimeters of water. We have extremely high stratification in this water column. And so what I would like to propose is that we're seeing suppression of turbulence, suppression of the ability of sediment to move throughout the water column that is due to this strong stratification in the water column that is damping our ability to suspend, to move around these sediments, which is why this is a dynamic, a quick process that we're seeing. So in summary, short time scales, these infragravity motions are important, are dynamically relevant for sediment transport between an estuary and a marsh at the very beginning of a tide when there's sediment in the water column and there's some stuff to resuspend on the marsh. The IG component, the infragravity component, is dominating this sort of deflux, but maybe being limited by salt stratification as salt enters the estuary. So it's a very short time scale, but I promise you that we have to think about short time scales, long time scales, and all of the time scales in between. So the question is, well, okay, now we've got some interesting short time scales that we hadn't thought about before. What about long time scale sediment dynamics? And here we think, I want to think a little bit more about inlet closure and what causes it and what we're seeing. So here's the Rio Aconcagua in central Chile. There's the Pescadero estuary in central California. Of my favorite estuaries, there's a couple of them. And what you can see in both of these images is that there's sometimes the inlet is open, sometimes the inlet is closed. Sometimes the inlet is very closed, and you can see here the water is green. It's just a Google Earth image picture, but a lot of these estuaries in central California, central Chile, you can actually go and see bright green water, high salinity, and some sort of algal blooms happening. So Dane and John Largier figured out what closes inlets, and it's scour versus sediment closing. And so big waves are going to push sediment on shore, and we can scour out any of these estuarine inlets with a combination of river flow, which is the obvious upstream component, but also with the tidal flow. So if we have a big tidal flow, that's going to cause a very high velocity, also scouring out the inlet. So Dane quantified that scour, the inlet flow, as the sum of the river flow plus a tidal prism. So it's got a bit of a conservation of mass here, where the tidal elevation multiplied by the area divided by time. So we've got basically a river flow and a tidal discharge that are going through the inlet. And in his work, we might have inlet closure when the waves are big and the inlet flow is small, and it's unlikely when the opposite is true. So thinking about this in terms of estuaries in Chile, we want to analyze, we want to look at these three terms and also come up with a data set of inlet closure. So Dane had a really had an expert local who just was making notes for 35 years or something. But the rest of us don't have that. But we do have satellites. And so there's been some work recently to look at inlet closure from a remote sensing perspective. There's a nice toolbox built on top of the COSAT that looks at inlet state. And so that's what we've done. We've looked at the Aconcagua estuary because it plays very well with this method. And so we can see here is a satellite image, and this is a water indice. And you can see clearly that there's a connection between the estuary and the ocean. And on the other side, you can see clearly that there's no connection between the estuary and the ocean in the Aconcagua estuary in Central Chile. So if we use the whole Landsat record, we can go back to 85, really 86, I think, is the first time we get a good measurement here. And what we can see is that through most of the 80s, most of the 90s, part of the 2000s, the inlet of the Aconcagua estuary was almost always open. And starting about 2014, and then again in 2018, the inlet has been almost always closed. So here we've got a 38-year record of inlet dynamics that is showing a drastic change. So let's now think about what's happening over 30 years, or what's happening on these timescales that we can understand and predict with variability. So here's the same figure, but now I've got day of the year on the X, and I've got year on the Y, and so we can see in the winter region, the inlet is remaining mostly open, and we've got summer closure, but it never really occurred prior to about 2014. We had this dramatic transition. We're going to analyze these. We're going to look at these three terms to try to shake out what's happening. So first, wave climate. Waves are what are responsible for closing the inlet. So we've got a wave measurement point from a wave model at this point right here. And so there's a couple of different data sets on here, and I've got significant wave height and peak direction. And what we see is that maybe there's like a very slight trend in increasing wave height. However, we have plenty of days of waves that are big enough to close the estuary. And I'm actually going to go back. So if we look at this figure, if you were to go like another half a mile north, there's a small marsh estuary that almost always has the inlet closed. And so we know that the coast of California the coast of Chile is capable of closing inlets. We've got the wave climate to do so. And it's changing, but not that much. And so let's discard wave climate as a change and look at these other factors. So stream flow, here's that gauge at Romeral that I showed you earlier. We have a massive reduction in the stream flow since 2010. And that reduction in stream flow is drought related. So I mentioned Chile is in a massive drought, it's drought related, but it's also agriculture related. And this figure I love because I don't think that we would see it in California, but who knows. So here's the stream flow at Romeral, which is the surface river, the main channel of this river. And this is the year, who knows, probably 2022, 2021. And so in the winter months, we can see June, July, August, there's some stream flow. And in the summer months, we have this very, very peaky flow. And so what we're actually seeing here is there's peaks of stream flow on Sundays. And so presumably there's irrigation, people are irrigating Monday through Saturday, and then, or Monday through Friday, and then on the weekends, the irrigation, or maybe it's mining, I'm not even sure. But so instead of having a seasonal rainfall, seasonal precipitation, we have the seasonality plus the weekly, what day of the week is it? And also of note is that the stream flow is actually going down to zero for most of the week in summer months. So absolutely bonkers stream flow if you're trying to think about these kind of long-term processes. And so that's a little bit farther upstream. There's a stream gauge that was installed in this estuary in 2020, or not in estuary, but about 6 kilometers upstream. And what we can see there similarly is that part of the year there's some flow, and part of the year we've completely dried out the riverbed. So our river flow QR is essentially part of the year 0. So that term is not going to help us keep the inlet open. And finally, I want to look at this last term. So in the tidal prism, which also is not something that you would normally think about changing very often, we're in a watershed here that has agricultural influence. It's got populations, and it's got a stream. It's got a water center that's right at where it says Espada Cancun. And so we're actually drinking water that comes from just upstream of the inlet, about 2.5 kilometers upstream. And so it's not so good when the water turns salty. And so what we do in Chile when there's no water or it's going to get salty, well, we build dikes. So here, there's a couple of these 2 images on the left are water rights and how they've increased since 2010, how they increased over time, despite the lack of water. On the top right, there's a underwater well, or you can see groundwater depletion. And the bottom right here, we see a dike constructed. And so basically, Chile is saying, you know what? Whatever fresh water is going to make it down here, like we're going to make sure we capture it. So if you go through planet.com imagery, which I had an undergraduate do, you can see the presence of this dike at various points in the last 10 or so years. And so what we think is happening here is we're actually not only reducing the river flow to nothing, we're also reducing this tidal flow, because what we're doing is actually changing the size of the tidal flow, the tide that can be moving in and out of the estuary by basically just putting a dam in the way of the tide. And so in summary, what we're seeing here in this particular estuary are these anthropogenic influences and the drought, plus also some just kind of downstream construction of features that are limiting any sort of tidal exchange that might keep this estuary open. So implications. There's no fresh water getting to the coast. There's also not going to be any sediment getting to the coast. And so this is the Aconcagua estuary, but also this past year we saw the Maipo, which had never closed before, and it closed in January. This is the Rio Petorca estuary, which also was always open until about 2014, and has seen such depletion that we've got the main river channel right there. When we measured it in January, was 60 ppc. So we've got this massive change, but then also it's been flooding this week, and so there's a couple of river plumes in Secochile. So I'm going to leave these pictures as, what are we expecting? Where do we go from here? Some conclusions, again, things are temporal. There's a lot of scales of variability that we need to study. There's a lot of impacts of drought, climate change, and anthropogenic impacts, and a lot of space to try to understand these relations, and especially how does this begin to relate to water quality, how does it begin to relate to ecosystems, the future of plant species in coastal wetlands, the future of the coastline. Thank you for your attention. I'm happy to take questions.
For questions, I believe, and I'm not looking at Zoom. Is somebody looking at it, perhaps? Nobody's looking at Zoom? Okay.
I can look at Zoom.
You can Zoom there. See if any
Okay, there's a question. Chris,
oh, you want to take that one?
Chris, can you turn on telephone? Yeah, so Chris asks if, have you observed degradation in upstream water quality since 2018 or since the dam was built? Great question. In order to observe change in water quality, you have to have good measurements, and we don't have good measurements. We have just started these images that are here. If I can, so we've just started a project looking at the Ligo Petorca estuary and the Pichicuri, the Copcola estuaries in a semi-arid climate, really focusing on drought impacts. And so there we are measuring water quality, and so hopefully we'll have an answer to that. In this little estuary, there's the fish is called Lisa. I don't know what it is in English. And there's illegal poaching. There's no connection, but the fish seem to be okay. There seems to be oxygen. And so the guys go in. It's only about yay high, and so they go in waders and just basically shoot fish in a barrel. They go in with nets and fish for these species, for these fish in this estuary. The Aconcagua estuary, nobody fishes there, and partially because if you see right here, so there's the Esval, you can see, there's a petroleum refinery, and this is a petroleum refinery that's been there since the 50s, 60s, 70s, somewhere in there. And so nobody really says we want to drink whatever, or drink or eat what's coming out of the Aconcagua estuary. But certainly, yeah, I mean, we can easily track changes in salinity, less easily track changes in water quality, but it's something we're working on. In terms of these dams have been, there's a dam built in the Aconcagua. There's also a dam built in the Maipo estuary, and actually like some pretty big conflicts between the artisanal fishermen there, because they're relying on some species that are extreme and need that migration, and also need fresh water. And so there's actually, we have a whole slew of measurements in the Maipo estuary looking at different conditions and whether they have a dam here or whether they've moved it upstream, and hopefully forthcoming work on that.
Chileans are innovative, right? So
we have to.
I don't know if people know that there was a plan to do that for San Francisco Bay, to build a dam wall across the Golden Gate Bridge and turn it into a big freshwater lake, and we wouldn't have any water resource issue, right? It's beautiful. Anyway, that didn't happen. I think it was in the 1930s. Other questions, more seriously? Yeah, Will.
There's a lot of talk of y-direction dynamics for the breaching, like the river outflow and the waves coming in. Mm-hmm. Like how much would like an x-direction dynamic, such as long-shore transport, play a role in breaching? Like if there's a long enough route, hypothetically, like not enough sediment supply? Could there ever be some sort of compensation for breaching?
Yeah, so I'm not sure I'm going to answer the question that you're asking, but I'm going to answer a question that I feel like answering. Yeah, so in the literature, in the the studies of why do inlets close, there's the work says, okay, we have bars migrating onshore, and we also have this longshore transport. And so we present these as like here's the things that move sand around. But almost everything that I've seen where they actually were able to kind of nail down what caused this particular moment of closure, it's almost always the onshore component. There's yeah, I mean, so in farther south in Chile, there's a estuary called the Mataquito. It's a beautiful long bar, it's just like miles and miles. And the inlet, the river flows out at the top. But same thing if you have a disturbance. So the 2020 tsunami just wiped the whole bar out, and it grew back in the same form. And a couple weeks ago, the river burst out through kind of a narrower point. And we'll see what happens here mostly. So in terms, I mean, yeah, no, you're right. Yeah, no, I think it's a Mataquito and with the Viva. Oh, yeah, no, you're right. Right, so that one might have broken. So in terms of lagoon of closure, the longshore component doesn't seem to be that important. In terms of what actually is happening when we get these big storm events, then we need to think about three-dimensionality, and that's also a direction that I have ideas to go if anybody wants to do a master's or PhD in Chile. But so what happens when you get these big sediment deposition, these big sediment events, is basically you can transport mineral grade sediments offshore. Jonathan Warwick at USGS has done some nice work in one of the Southern California estuaries, where basically you get this big storm event and you're dumping all of these sediments out, and some, the fine stuff is going to float away, and the fine stuff is not going to help us in maintaining sand on the beach, but some fraction of that is beach grade sediment. And so what happens is, my understanding is that you basically dump a sandbar. And I have some colleagues who sent a picture of people surfing the Cahuil estuary last week, because you get a bar break, you dump sand, you get a bar break, and then these three-dimensional processes are either going to move that sand, depending on where you are in the depth of closure, you're going to move it back onshore, you're going to move it offshore, or you're going to move it. So yes, totally important. But in terms of inlet closure, no. And if you don't have questions, I'll ask questions. What do we need to be thinking about in terms of physics and relating to the species that are important, or relating to the vulnerability that we see in California and we're feeling, specifically whether it's like fresh water and salt water?
Thank you. Will might be able to speak to this a little better than I can, but one of the things that we're focusing on with respect to estuaries, freshwater output, and coastal ecosystems is kelp forests and kelp restoration. There seems to be some connection between kelp forests doing better where there are higher river outflows, and whether or not that's related to the seasonality of bar-built estuaries being breached or not is still something I think that we're trying to assess, but it's one of the many things that we're looking into, well, we can go outplant kelp here, but is it actually going to stay? And if we have a better idea of what the oceanographic conditions are that can help inform both the sites we choose and how we manage them.
So is there, obviously the oceanographic, the waves and the currents are important, but is there a minimum nutrient? You think that nutrients, river nutrients, could be a limiting factor?
Possibly. I don't think that's something our group is focused on too much, but yeah, definitely something else to consider.
Yeah, no, I mean, and I have this work on the Aconcagua. I think it's maybe somewhere on this slide. I'd like to talk about. There's no nutrient delivery if there's no water delivery. But that's sort of me raising my hands and saying, I think that this is an important thing. The actual physical or actual biological response for something called water. Yeah,
So what I wanted to ask is, can you go back to the drone images of the Maipo? So my simple paraphrasing of what you're seeing there is that as the tide comes in, the infragravity waves stir up the sediment and land up pushing them onto the mud flats and the marshes and things. So you build the wetlands and marshes. That's pretty cool. But then you showed the stratification happening. So I have two questions. The one is more serious and the other is more provocative. The first is you showed two images when you eventually.
I lost it. Yeah. No,
Yeah, no worries.
Open.
There's a lot of things in your
Is that right? No, usually they hide it, but I accidentally or no, I think that this display uncollapsed.
So if you can get the slide where you show the stratification, if everybody's remembering that, you know, those infragravity waves like stirring up the sediment, pushing it up, but then you found that it only happened for a while, and the stratification sort of came in. The serious question is why it hadn't got much deeper or anything. There was a sudden change in stratification. And then the more provocative question is, if we had no freshwater flow in an estuary, you'd not have stratification, and you could keep building your wetlands through the whole tidal cycle. That'd be way better.
No.
Okay.
So
first.
So I'll answer the provocative question first. With this picture. I'm going to turn off all the lights so you can just fully appreciate. Thailand tourism front, we've got oceanic, we've got salt water that's coming in and actually plunging below this little V shape that we see here. And it's very clear to me that the river water is turbid and the ocean water is not turbid, right? So if we don't have any fresh water coming in, then we're relying on this oceanic water, and that's not going to grow any marshes because we don't have any fine sediments coming in with oceanic water. Yes, could we be building up beaches? Sure. And then that's I defer to the beach and the dune people to think about beach and dune migration. But we do need the river for the sediments that are in for wetland species. Is that okay? In terms of stratification, what's actually happening? Is it a coincidence that we're seeing as this is highly stratified water, and so basically we've got this salt that's starting to move on, and it moves on similarly on these little infragravity motions. So you can see here the salinity coming up, and it peaks and it goes down, and then it starts to peak, and I really wish that I had this set of moments in time instead of, well, I should have just stayed out there longer, but it was cold and we weren't sure what motions we were getting. So we've got these salt that's moving onshore and offshore, and by shore I mean the wetland, and then we see this high stratification. So what's happening here that we're seeing lower turbidity? It could be suppression of turbulence, and so we're actually not able to resuspend things. I might be measuring in the top where it's the water's got less stuff in it. I might be measuring. So you can imagine that maybe my measurements are above the red line, the red area above the salty water, and so all of the sediment resuspension is occurring below. Various hypotheses, which is probably more provocative.
Great, thanks, Megan. I think time-wise we need to wrap it up, and there are. Well, thank you again very much for your seminar.